All right, everybody, come on in. I've got a little something to show you. You might not want to miss this. All right, we've got our first session for, what is this? Thursday. All right. Well, how's everybody doing? Come on, how's everybody doing? All right. Anyone here that was out at the shop at 3 o'clock in the morning? There we go. All right. How was it? Great. All right. The response was great. So let's just start with a little something right here.
Professional. Don't try that at home. Thanks.
Nice. All right. Some elevate brushes in there. So I'd like to introduce a duo here, and Adam Clark is going to be leading the discussion here this morning. Adam is the VP of the Houston EAA, the Electric Automobile Association. He's also the regional director for Texas for NEDRA, the National Electric Drag Racing Association. He is currently building a 1968 VW Squareback. He has a business background, and he is part of the Lone Star EV racing team with John Metric. He's the wingman. John is the wingman today for Adam. Adam is going to be running the show, and I just want to hand this off to Adam and give him a big round of applause at 9 o'clock in the morning. EVCON.
It's a Mac, Adam.
Yep.
Nice.
Okay, good morning, everybody.
Good morning.
So, this is my second EVCon. It's great to see everybody again. Had a great time last year, so far having a great time this year. And one of the things that it's always impressed me is how little I know about EVs, even after 4 years, compared to everybody in the crowd here. I learn a lot every year. I personally try to learn as much as I can from you guys, because you guys are the the top of the industry. What Jack described yesterday, or in the opening day, about us being early adopters. We're not even early adopters yet. We're not even that far. We're the tinkerers. We're the experts. And I think we've got a long way to go yet. But we've got a great opportunity here at the very beginning to make a lot out of this new EV industry, and that's primarily what my presentation is about. Yes, we do electric drag racing, but there's a lot of opportunity, a lot of business opportunity for anybody that has the knowledge and the interest to make something of a business out of this industry. So you guys are the experts in your field. You've got material guys, you've got double E's. I'm probably one of about 4 non-engineers in this whole room. So you guys have a great opportunity to do something in this industry, and just that's what my presentation that I hope that I can express to you guys. So a little bit of background about Lone Star EV Performance. John started out with his first build, DC Plasma. That was the red Fiero that many of you guys have seen. And about 2.5 or so years ago, we decided, I met up with him about 3 years ago. We did the Fiero racing for a little while, and it wasn't too long after that we decided to do a new car. We bought the Miata over the course of about 6 months or so. We built the car, and for the last 1.5 years, maybe a little more, we've been doing the racing in the Miata, and we've set a couple of world records, gone up to the track, impressed quite a few people. Most people cannot even believe that it's electric, given the power that we're putting down and the times we're doing. Every time out on the track, we beat the gas guys. I mean, it's not even close most of the time. So I think that as we get out there and more people see what we're doing, there's a big opportunity, not just for EVs in general, but EV racing specifically. So most of my presentation is going to be geared towards, in the context of racing. There'll be a few things that we'll touch on that may not be necessarily true for average day-to-day driving, but they're particularly true when it comes to racing. So I wanted to start off this presentation with a quote. This was a recent article about how EVs are selling better than hybrids did, a few years after hybrids had been released. And so he says, so I'm not too worried about electric cars. Like solar panels, they'll be a small part of the market at first, reserved for early adopters and visionaries, and over time, as prices drop and technology gets refined, they'll take over. Why? Because they're better than what we have now, and so are EVs. So it's a good way of looking at it in this early stage of the game, where we have a better product. It's obvious. Every time we talk to someone about EVs, we talk about how much better they are than their gas counterparts. Everybody has different reasons why they switch to EVs, but at the end of the day, it's a better technology. So over time, more and more people will catch on to that and see the future. So here's a background as we get 0 to 60 in less than a second. They did a quarter mile in 6.9 seconds at just over 200 miles an hour. The official record is 201 miles an hour in a quarter mile on an electric motorcycle. That is insane. I wouldn't even consider that. But when you consider you got one motor, one controller, 400 volts of lithium, around 800 horsepower. The whole thing weighs, give or take a little bit, 800 pounds. I mean, it's a marvel of engineering. All these dragsters are a marvel of engineering. Here's Don Garlitz's dragster, and a lot of what he's done is kind of top secret, but some of it isn't. So he's running 6 small GE DC motors. Up until recently, he's been using 3 Zilla 2Ks, and now he's upgraded to 6. I don't know if he's made a run yet using 6, but that's his plan. 400 volt battery pack, 2,000 horsepower, 2,200 pounds. And his goal is to get 200 miles an hour in the quarter mile. Now, Don Garlitz was actually the first drag racer to go 200 miles an hour in a gasoline dragster. So now he wants to be the first one to go over 200 miles an hour in an electric dragster. So this year will be the 50th anniversary of when he broke 200 miles an hour in a gas dragster. So it'll be really, really cool to see if he can do that, 50 years to the year, breaking 200 miles an hour in an electric dragster. And of course, this is us. This guy right here, he's real familiar. He looks familiar. This is our friend Keith. Big fan of racing, longtime Ford Mustang racer. This guy, kind of hard to see, but this is what. Yeah, this is actually what John Metric looks like without his cowboy hat. And this is John's son Nate, who's been totally instrumental in this whole racing team. Doesn't get a lot of camera time. Probably doesn't even want lots of camera time. But he's done so much to help John get the car ready, get the car out to the track. And he lives an hour away from me, so I can't always be there to help him, but Nate has always been there to help him. So we've got 2 9-inch DC motors, Hellwig Racing brushes. Yes, our sponsor Tom, instrumental. All this power would never happen without these brushes. 2 Zilla 2Ks, 375 volt battery pack, roughly 800 horsepower, 2,200 pounds, 0 to 60, really fast. And our personal best, 8.9 in the quarter mile at almost 150. So if I could go back for just a moment. One of the interesting things about these 3 cars is they're all DC motors, and they're all Zilla controllers. So that's something interesting to think about. Is in the drag racing world, DC motors are where it's at. Now that'll stay that way for a little while. We hope to change that shortly, but for up until now, that has been the gold standard, is DC motors, Zilla controllers. But I wanted to talk about other racing opportunities and other EV technologies. So, motorcycle racing. Nissan made this Delta Wing a couple of years ago. They've done some exhibition runs over at Le Mans. Pretty impressive. They're not beating anybody yet, but they're exceeding expectations, and they'll progress every year, a little bit every year. Formula E is starting this year. I'm real anxious to see what they're going to do with that. It's real exciting technology. Hopefully they'll get the public out to see what they're doing. And with EV racing and EVs in general, it's all about visibility, getting the public to see what's going on in this industry. Here's the Drayson race car. Drayson is former high-up guy in the British Parliament. He decided he wanted to start a race team. Okay. So he spent a bunch of money, made an all-electric race car, and he just recently set a record, 0 to 1 mile at 200 miles an hour. Real impressive car. Big money though. And these are some small time guys. Entropy Racing makes a little electric car like this. A little bit bigger car is this race team right here. And then this guy made an electric go-kart. And I'll touch on this a little bit later. TTGXP, electric motorcycles. They've been real impressive. They've been racing for a couple of years. And they're right up there with the gas bikes all the time. And in fact, the fastest motorcycle on Pikes Peak this year was an electric motorcycle. Does anybody know what the 4th fastest car was on Pikes Peak? It was actually an EV. So for the 100 or so years that they've been doing Pikes Peak, electric vehicles are already the number 4 car. Within a couple of years, electrics might finish 1, 2, 3 at Pikes Peak. I mean, that would be incredible. So that's really something to look forward to. The big money racing is, as I call it, has its place. Formula One, for example, Formula One cars look a lot like that. That's why they. Okay, so no more pointer. So the Formula E cars were specifically designed to look similar to the Formula One cars. The racing car up on the left, real expensive car. I don't think he's got a harem of people. Army of 1,000 people making that car happen. And then there's the 24-hour Le Mans prototype series. Toyota, this is actually a hybrid, not an electric. So the Formula E starts this year in October, and it'll be really interesting to see how well the reception is for Formula E. This will be its inaugural year, and the role that the big money guys have is that this level of racing has always been a proving ground for the OEMs. A lot of technology that you find in today's cars actually were initially developed in the racing world. So this, in a way, corresponds to some of the opportunities that you guys might see in the electric industry. You've got an opportunity to possibly approach teams like this with ideas that you guys have come up with and say, hey, I've got a product. I want you to try this. It's better than what you've got now. And that's how these teams operate within the rules of the racing series, of course. But then there's the average guy racing, and I see a group of people like us, and I see the average car racing as being a big opportunity. So SCCA, Sports Car Club of America, huge club, tens of thousands of guys around the country that do racing. NASA, National Auto Sports Association, another smaller group. And every year, I think this is the 4th year now, they've done a big race down in Laguna Seca. It's not called Laguna Seca anymore, it's Mazda Raceway or something like that. But they have a refuel event where you have hybrids and electrics, and they go race out on the track along with maybe not at the same time, but at least on the same weekend as some of the gas cars. And every year they get more and more cars out there. So that's more and more visibility every year. And there's opportunities for us to create new products, put them on a car, put that car on the track, and show people what we can do. So these two things together, the average guy racing and the big money racing, there's opportunities here in a lot of different fields. material science is probably the biggest one. Lightening the car, getting more performance out of the materials and components that we're already using. The Formula One, if you're not familiar with that, it's technologically amazing what they're doing with these cars. One of the things that I jotted down is the electric turbocharger, and that's an amazing opportunity. Turbochargers typically run on the exhaust gases, but this one is a combination of an electric motor connected to the turbocharger. So a bunch of electronic wizardry goes on, and they're able to maintain much higher power without being too much drag on the engine. The other opportunities would be energy management software. When Colin did his presentation yesterday about the computer hacking and all that, the software writing, the code writing, there's a lot of things that are being unlocked, just a lot of power that's being unlocked just through software design in today's hardware. So that's a big opportunity. If you know how to do that, turn your head to Colin. He's probably going to be the richest guy in the room in 10 years. It's amazing.
If he turns evil, goes out to the bank, I'm sure.
So other opportunities, you can look at the shapes of these cars. That was endless hours of aerodynamic testing. There's a career in that. There's a career in making those body panels out of carbon fiber or some other advanced material that someone out there might think of. And all of these play a role in what can be done in the electric industry. Well, before I get to batteries. So a little bit of, I wanted to touch on the Formula E a little bit more, because that's going to be the most visible electric racing this year, is when Formula E gets underway. The power that it's going to put out is actually pretty modest compared to the regular Formula One, but it's still pretty impressive. It's going to be a 133 kW drivetrain with 67 extra kW with a push-to-pass button. So that's a pretty interesting idea. If you want to pass somebody, you just push a button, and then for a certain number of seconds, you get that extra power. It's an 800 kilogram car, and up to 200 of those kilograms can be the battery. And that's 800 kilograms with the driver. So a lot of engineering goes into that material science.
Hey, Alan,
Yes.
September 10th is the start in Beijing. They changed the schedule. They've added Beijing.
Oh, they've added Beijing?
It's September 10th.
Oh, 10th, okay. The 0 to 60 time is about 3 seconds, which is a little bit slower than the regular Formula One. And the top speed is going to be a little bit slower as well, because they're racing on city streets. But it'll ultimately it should be just as exciting. They run an 800 volt battery pack with a two-speed transmission. And one of the best parts about it is that these first 2 years, they've got a set body, a set drivetrain, a set battery pack, and everybody has to use the same thing. But in 2 years, they're going to open it up. Anybody can build a body, anybody can build a drivetrain, anybody can supply batteries. So there's an opportunity there to get new products out on the market and vie for that leading spot with these big race teams. If you've got a great battery idea, you can go talk to race teams like that. possibly get your battery on the market. So speaking of batteries, one of the things I wanted to talk about is the batteries themselves. So this is just an overall view of some of the batteries. Everybody's familiar with the prismatic and the iron phosphate. So what I want to do is kind of show you, in the context of racing, what the various specifications are for these batteries. So a typical C rate for iron phosphate might be around 5. Some might get a little bit more, but it's around 5. The weight per kilowatt is around 13 to 40 pounds per kilowatt, depending on your connectors and how much plastic is around those battery cells. And then the weight per kilowatt hour is about 17 to 26. Pretty good. It's good for a conversion car. It'll get you the range you need. But for racing, watt hours per kilogram is still relatively low, 83 to 126, depending on what brand you buy. And then there's some pouch cells. We got a picture of Interdel, and we've got a picture of A123 batteries. Peak C rate is a little bit higher. Weight per kilogram is a little bit lower. Weight per kilowatt hour is a little bit lower. And the weight per kilogram, 100 to 115. Not bad. Not bad. There's some applications for this type of chemistry. For drag racing, there's a couple people that are using the A123s, and they're pretty successful. Later we'll get into what some of the other applications would be for this kind of battery. But what we've been using is the high rate pouch cells. And right now in the car we have 150C pouch cells. 200C is on the way really soon. The weight per kilowatt is, if you remember where we started 10 times this much weight per kilowatt. So our batteries at 100C, that's continuous. So we're racing 150C now, peak, a little bit more than 100C continuous. Drag racing use, yeah, drag racing continuous. So 1/4 to 1/2 pound per kilowatt. And this is the 144 to 223. You'll want to remember that number for a little bit later in the presentation. So as we get higher into these C rates, one of the things that often comes up in racing is supercapacitors. So I did want to touch on that for a moment. I've got a couple of quotes here. Williams Engineering is the company that makes the battery pack for Formula E. And he was, at one time he said, "Racing improves the breed, and we should expect higher energy density batteries thanks to Formula E." Yeah, generally, that'll be true. Toyota Le Mans car, that's the hybrid that I showed you a picture of, the red and white one. Someone on their team, or somebody doing an article on the team, said that the race car uses supercapacitors because they're effective at storing energy created when the vehicle is under braking, only to quickly redistribute it on demand for rapid acceleration. And they were saying that this technology might be available in the Prius in the next 5 years. That's cool. That happens all the time. Technology starts on the racetrack and ends up at the OEM. So that car has supercapacitors. Maxwell is a big company that makes supercapacitors or ultracapacitors, and one of their market experts, I had to put these quotes in because efficiencies just off the wall. But, supercapacitors can destroy the lithium-ion market. Supercapacitors are improving faster than lithium-ion batteries. Maxwell's new supercapacitor has 7.7 watt-hours per kilogram. Their top secret nanotube technologies have demonstrated supercapacitors with 35 watt-hours per kilogram, saying that 500 watt-hours per kilogram might be achievable. And the ultra top secret graphene supercapacitor developers are targeting, haven't reached it yet, but they're targeting 200 watt-hours per kilogram. This is what we've been using for 2 years. And it's getting better. So the batteries we're using, they're already better than what the supercapacitor guys hope for. So our batteries are becoming more and more like capacitors all the time. So who knows what the supercapacitor guys will develop in the future, but we're already using batteries that are better than they're hoping for with their supercapacitors. So don't know what's going to happen there, but we'll just keep using the batteries we've got. The opportunities for us, the entrepreneurial opportunities, might show themselves as a supplier to OEMs. And one of the things that Jack has talked about many times in his video is how all these OEMs and OEM suppliers have gone under. So there might be an opportunity to create some value in just a new way of thinking of something. So one of the videos he did is when he disassembled those Renault packs, and a third of the weight was just superfluous stuff. It was just completely unnecessary. So for the conversion market, you don't need all that extra stuff. For racing, you might want some of the extra rigidity. But there's new opportunities, new ways for you guys to think about how packaging might be done, how you might sell this to another company. One of the other parts of value is quality of what you have. And so John put together this little chart following what we've had over the last 4 or 5 years with our high C-rate pouch cells. So in 2009, the Fiero was running 75C pouch cells. In 2010, it was 90. In 2011, it was 100. 2012, it was about 120. And in 2013, we upgraded to the current 150C that we're using now. And here in 2014, we've got 200C on the way. Those are peak numbers. The drag race through these cycles is a little bit lower than that. But what's interesting is the quality numbers. In 2009, John guessed about 1 in 100 were cell failures. About 3 years ago, it was 1 in 200. Last year is about 1 in 500, and he says that now we've sold a few thousand of these cells, and now the numbers are more like 1 in 1,000 or more of these are bad cells. So here's another opportunity, make a better quality product, and you might not go under. Next is motors. A lot of familiar looking motors up here. UPM, Warp, Siemens, HP EVS. This nice shiny one here in the middle, this is a Remy, real expensive motor. And then down here on the right is it it looks as big as the others, but it's not. It's a brushless DC motor. EVTB actually sells them on their website. So I wanted to talk about all of this, mind you, is in the context of racing. So I wanted to talk about some of the different kinds of motors. The Series 1 brush motor, it handles a lot of amps, but for a relatively short period of time. A lot of amps makes lots of torque. So it's a great way to go really fast on a budget if you're building a drag car. If you're not building a drag car, some of the negatives are that it's not as efficient, and it's relatively easy to overheat, and with heat you also have brush maintenance and other issues to think about. The brushless DC, it's relatively inexpensive technology, but if you see these two motors side by side, you'll see that that these are more suitable for small things. You remember seeing that picture of the guy that made the go-kart brushless DC motor. So there's opportunities. It may not be suitable for a full-size car, but if you want to get out there and sell some electric go-karts, that might be something worth considering. AC induction motors, they've got a few different standard torque curves, actually 4 of them. So there's some opportunities there to actually choose a motor that's suitable for your application. And one of the other advantages is they're everywhere. AC induction motors are everywhere. If you want an AC motor, they're most affordable because they are everywhere. You can pick them up just about anywhere. And they run higher voltages, which improves efficiency, and also you don't have to run as many amps if you run higher voltages. And they go up to like 95% efficient or something like that. A little bit more than the DC motor. Some of the negatives are that compared to DC controllers, the controllers are a little bit more complicated, a little bit more expensive, and with the controllers that are currently available, they don't offer near enough power for drag racing applications. So that's one of the negatives. Depending on what application you are for any non-drag racing that you'll be doing, there's probably some suitable controllers out there for you. The permanent magnet AC, a little bit more efficient than the induction motors. They have a little bit bigger RPM range. They're a little bit smaller, a little bit lighter, but if you get them too hot, they'll demagnetize, and if you're doing any kind of road racing, heat is always the worst thing. That's what you want to manage more than just about anything else is the heat. And so you run the risk. We haven't done any road course racing yet, but racing is all about pushing the limits. So we'll just have to see how far you can push a permanent magnet motor before it demagnetizes. And the controllers for a permanent magnet motor are a little bit more complicated, a little bit more expensive. So one of the things I also mentioned servo motors, but that's not really an option for racing. The servo motors on paper look attractive, but they're not really available. So the induction motors and the permanent magnet motors, those are the ones that we have access to by and large. So a study was done, one of many I'm sure, compared the use of induction motors and permanent magnet motors in hybrids. And so they did a city test, they did a rural test, and they did a highway test with different driving conditions. And they want to see how much more efficient the permanent magnet motor was over the induction and what other applications it might have. So So for the city driving, the permanent magnet motor was a lot more efficient, 27% more efficient. So it would go 27% farther than the same vehicle with the induction motor. But that's slow speed, city driving, lots of stops, stuff like that. But for the rural cycle and for the highway speed cycle, there was almost no difference between the induction motor and the permanent magnet motor. So granted, it's for hybrid use, not pure electric use, so there might be a little bit of a difference there. But the point is that in the context of racing, you will be going a little bit faster. You'll be doing more stops, more accelerations, and your overall average speed is going to be a little higher. So this study that shows that those two motor technologies actually got a little bit closer together with the higher speeds. That was interesting to read. The difference between those two driving cycles was only 1%. But in their summary, they said that in highly variable cycles, the permanent magnet motor will be able to outperform induction motors in specifications that have significant speed changes. These speed changes should be more frequent and have a high change in magnitude. So that leads you to think that road course racing might be a good application for permanent magnet motors. So anybody interested in building a road course electric race car, you might want to consider that, and let us know if you demagnetize your motor. The servo motor, I couldn't find many pros for that motor. On paper, it sounds great, but it's about 10 to 20 times the cost of the permanent magnet or the induction motors, and it's an extremely complicated controller. So I don't know if that has any application in what small budget guys like us could use. The controllers got some DC controllers, got some AC controllers, the DMOC in the middle, everybody recognizes. So again, this is all in the context of racing. The Zilla 2K puts out roughly 300 kW to the motor, because the motor is limited to about 200 volts. The Shiva puts out about 500 kW to the motor, because again, the motor is limited to about 200 volts. That's quite a bit of power. Put two motors and two controllers in a car, you're going to take off. That's a lot of power. The AC motor controllers, a little bit different story. The DMOC up here at the top left, 53 kW continuous, 118 kW peak, up to 400 volts. 400 volts, that's respectable. But a little bit lacking in the power conversion for drag race applications. Reinhardt, a little bit more powerful. They've got a 150 kW version, pretty respectable. Small, lightweight road course cars could probably make use of a controller like that. The Scott Drive, which I was surprised to see that at Jack's shop. On the web, it looks a lot smaller than it actually is. But it puts out about 100 kW continuous or 150 peak. And then Curtis, they make looks like they're DC controller. I'm not sure how that got there on the AC slide. But HP EVS has their Curtis controller over there, and about 65 to 75 kW for the 144 volt model. Not bad. Great for conversion cars. But we need a little bit more power for drag racing. So what do you do if you want more power? So you can do more volts, you can do more amps, you can do more amps and volts, You can do more cooling. Cooling is the enemy, or heat is the enemy, so you want cooling. So if you can make your components run cooler, you can run them higher. But the more power you create, the more electrical noise you also create, so you got to look at that as well. So taking a break from the controllers here for a moment, get back to some of the opportunities that you might have in this new EV industry. These little nanotubes, that's my picture for material science. There's so many materials that can be explored, and there might be an application for it. Material science degrees is really hot right now, because that's the future in a lot of industries, investigating new technologies, new materials. I'm not that technically inclined, so my profession of choice is the welding. Opportunities there as well. Maybe not with your TIG welder. You're not going to be getting many OEM jobs doing TIG welding. They've got robots for that. But apart from the OEMs, if you want to do a racing business, TIG welding is where it's at. You can make cars out of, you can make various parts out of aluminum, magnesium, titanium, all of which can be TIG welded. This one up here, I have no idea what that means, but I bet you Colin does. That is software writing. After his presentation yesterday, anybody who knows how to do that, you can see some of the opportunities in the EV industry that someone like that has. This thing over here that looks vaguely like a car, that's actually a carbon fiber shell for some European car, I believe. And so that's an opportunity for material science, lightening the weight of the car. Carbon fiber is one of those ways. If you know how to work with carbon fiber, and you've got some great. Oh, okay. Okay. Is that better? Mm-hmm. So if you know how to work with carbon fiber, or if you think you've got some other idea that's better than carbon fiber, you might have an opportunity there. Aerodynamics, that's a big deal. If you know how to, if you've got this great idea for a cool shaped car that no one else has done, build one, sell it. That's a great opportunity. So our niche market is racing, but there's a lot of other niche markets out there. So one of the opportunities could be what we've done with our DC controller. This is a DC converter. This is a DC converter that we sell under our own brand name. Louder? Sound like I'm too loud. So this is the DC-DC converter that we sell under our own brand name. I know the original designer of this, and he originally designed it for industrial applications. And it originally had 48 volt output, up to 720 volts in, and we said, this is cool, this is really nice, but it doesn't work for what we want to do. Can you change it to 12 volts out? And he said, sure, no problem. So we changed the design a little bit, took it from air cooling to water cooling, made a nice case for us, so we got it out here on the table. Got it out on the table. So now we've essentially repurposed an industrial unit for EV use. So that's another opportunity. Lots of things out there that could be repurposed for the EV industry. You just got to go out there and find them and sell it. So a little bit about our DC converter. 100 amps continuous out, up to 720 volts in. That's our low voltage model. We're currently developing a high voltage model to go with our controller, which I'll talk about in just a moment. The case, the aluminum case that you see out there on the table is new. What we've done in the past is a polycarbonate case where you can see the inside of the converter. So the AC motor controller, this is our new creation. The model that you see over here on the cart, this is our prototype. We've done bench testing on it, but we haven't done car testing yet. That'll happen after the convention. 1400 amp continuous IGBT. That's all day long for as much battery as you've got. It'll do it. 1400 amps. 1200 volts in, up to 1200 volts. If you use really stiff batteries, the high C-rate batteries that we have, that 1200 volt pack might sag to 1050, 1100, around 1000, something like that. So definitely high power. So little description here. This box right here, this is the capacitor box. This is where most of the capacitors are. This is the power unit where the cooling and the IGBTs and the DC bus bar are. And then this box right here, this is where all the electronics are. The current sensor, the circuit boards, the gate drivers, all of that is in that. And you would mount that close to the motor. You would mount the capacitor box as reasonably close as you can to the main power unit. But essentially all three of these components would be mounted under the hood as close as you can to the motor. It was originally intended to be a plug-and-play controller. Any AC induction motor that you can get manufacturer specs on, you just type those specs into the setup menu, and the controller will work with that motor. We've got 3 different power levels in mind. The power levels are based not so much on the IGBTs themselves, because those don't change, but the amount of capacitance and a few other small considerations is where you get your 3 different power levels. The smallest is going to be 300 peak, the middle one will be a megawatt, and the top end will be 1.5 megawatts output. So what on earth would you need 100 or 1.5 megawatt controller?
Time travel.
So if the lighting's not great, if you can see this little blue and white smudge right here, this is a guy. And at the looks of him, probably a pretty big guy. That's not the biggest dump truck in the world. The biggest dump truck in the world is actually a hybrid. It's got 8 wheels, 2 axles, 4 wheels on each axle. Each wheel, each corner, so I guess it's each pair of wheels, has 4 motors, 4 electric motors. And those motors are driven by a generator. And the generator is driven by a 23,000 horsepower diesel motor. That's a lot of power. But the point is that the drive wheels are electrically powered. Our controller can't do that. Maybe one of these days, but not quite yet. But there are applications outside of racing. If you want to invent something crazy like a 1.5 megawatt controller, you can find non-EV applications for that, and that's yet another entrepreneurial opportunity for you guys to do something that you like to do, electric motors, electric controllers, whatever, and find some other use for it. On a side note about the controllers, I found this and I had to put it in. Quote, GM is developing a next generation power inverter capable of 55 kW peak, 30 kW continuous. GM is almost 2/3 of the way through the $16.6 million project, which began in October 2011 and is scheduled to be finished in January 2016. I almost couldn't think of what to say after reading that the first time. So the new inverter will bring the cost of power electronics down to 3.3 pounds per kilowatt. Power density to 13.4 kilowatts per year. John and I will have to do the math to figure out what hours will do. But as a ratio, we probably did better than GM at about 1/1,000,000th of the budget. So we'll see. So there's opportunities like that. You look at companies like GM. Jack doesn't particularly like GM. He makes that very clear in some of his videos. If you look at what GM's doing, you say, "You guys don't know what they're doing." You can say, "I know what I'm doing." And you can go to companies like GM and sell them your new product. It may not be very easy to get GM's ear, but there's plenty of other companies out there that are interested in new technology and new inventions. Oh yeah, it has to be efficiency greater than 94%. Oh, are we? I'm sorry. I do one last slide real quick. Last slide. Actually, this is officially the last slide. Other applications. This is not the HP EVS Corvette, but it looks a lot like it. Last year, I rode in the car with Brian, and I asked him if part of the design consideration was making the performance equal to the real Corvette. And he said, no, that wasn't the top design priority. But if you wanted to put a 500 horsepower controller into it, then you would have the factory performance. Actually, it would only take about 350 horsepower. But sports car, that's a great application for a higher horsepower AC motor. Pickup trucks, either hybrid or pure electric, great opportunity for higher powered AC controller. Medium duty trucks, shuttle buses, all opportunities. And there are companies out there right now making pure electric medium duty trucks. And we'll wait and see what the market acceptance for that is. The last two pictures, if you're not familiar with drag racing, this is a top Fuel Dragster. This is a funny car. A lot of people chuckled when you saw the 1.5 megawatts. Our lowest powered controller, 500 kW, is 10 times more powerful than the average AC controller. Our top end AC controller is 3 times more powerful than that. Yet it's only 1/5 as powerful as the engine in these top Fuel Dragsters. We would need 5 of those 1.5 megawatt controllers and probably 5 motors to equal the power of one big block V8 with nitromethane and a giant supercharger on top of it. But the point is that in the context of racing, there's a long way to go. There's opportunities for you guys to invent all sorts of crazy stuff. And whether it be in the realm of racing or some other application, you guys are the best in the field. Whatever you guys can think of, there's a market for it. It may not be in the EV industry. Maybe you can find some other application for it. There's a market for it. Anything you guys can think of, there's a market for it.
I have a quick question.
Sure.
Is your, let's say your 500 kilowatt controller, does that have a price, or you can only make those available to OEMs?
We're still working on that. We're still working on the price. It's pre-production at this point. We still need to do vehicle testing. I would think
anticipate the price like raise.
after the presentation, we can talk with John about some little bit narrowed down numbers. But yeah, pre-production at this point, it will be available to anybody who wants it. It's not just OEMs.
Okay. Real quick, anybody? Back in the corner. Go.
Real quick question, chemistry on the new power cells.
Lithium cobalt. All of the pouch cells that we've been using, they've all been some derivative of cobalt. Yes.
What motors do you intend to use your controller with?
So we do have an AC motor. It's going to be more or less a package deal. We would prefer to sell the controller with that AC motor. But like I said earlier, the intention is to be plug and play. Any motor that the manufacturer is willing to give you the data for, any motor that comes with a nameplate, type in the data on that nameplate, and it works with that motor.
So you're in a private line motor? Is that
Yes.
EVCON?
That would thank you for a great session.